Unlocking big data potential. How Nielsen transformed their processing with Amazon EKS. In the fast-paced world of advertising technology, Nielsen Marketing Cloud stands out as a powerhouse, processing a staggering 25 terabytes of data and 30 billion events every single day. However, as their data demands skyrocketed, so did the challenges of efficiently scaling their Apache Spark workloads. Imagine a scenario where adding more instances to a cluster actually slows down performance. That's exactly what Nielsen's team faced. As they expanded their cluster, they noticed a troubling trend. The performance per instance began to decline, leading to increased costs for processing each gigabyte of data. To make matters worse, they also dealt with data skew issues, where uneven data distribution across partitions created bottlenecks, sometimes even causing cluster failures. In this article, we'll take you on a journey through Nielsen's innovative transformation as they built a robust and scalable architecture that embraced linear scaling. We'll start by diving into the initial hurdles they encountered and the root causes behind these challenges. Then, we'll explore their groundbreaking solution. Running Spark on Amazon Elastic Kubernetes Service, EKS, while adopting serverless concepts. #### from Spark clusters to Spark pods on Amazon EKS. Nielsen's marketing cloud architecture initially relied on a traditional Spark cluster hosted on Amazon EMR, processing a continuous influx of files of varying sizes. However, as both the data volume and cluster size expanded, the team observed a concerning drop in performance per instance. This decline not only slowed down processing but also drove costs up, while data skew occasionally led to production issues. The team pinpointed the problem. As the cluster grew, the number of remote shuffles between instances increased. Remote shuffle, a process in Spark that redistributes data across partitions, involves significant data transfer over the network and can become a major bottleneck. Realizing the streaming nature of their data, Nielsen decided to process it in smaller batches, allowing them to rely less on large Spark clusters and instead utilize smaller ones. To combat performance degradation, the team shifted their strategy from scaling up a single Spark cluster to scaling out with multiple local mode Spark clusters. Single-node clusters, running on Amazon EKS. This approach not only improved performance for small analytics workloads but also eliminated the need for remote shuffles, as each local mode handled a limited amount of data independently. Additionally, the pods on Amazon EKS could dynamically scale up and down based on workload, allowing Nielsen to optimize resource usage and reduce costs. The result? A solution that scales linearly, is 55% cheaper, and processes data faster even during peak loads. #### the importance of shuffle. Remote shuffle becomes necessary when data needs to be exchanged between Spark instances, especially during transformations like joins or repartitions. Unfortunately, remote shuffles are significantly slower than in-memory computations, often adding 100 to 200% to total processing time. As Nielsen's cluster size increased, so did the amount of data shuffled, leading to inefficiencies. The team hypothesized that minimizing shuffle could lead to substantial performance improvements. By implementing serverless patterns, they drastically reduced the size of each cluster, while increasing the number of smaller clusters to compensate for the reduced capacity. This strategy aimed to eliminate remote shuffle entirely for each data work item. #### designing a serverless-inspired system. Nielsen's team crafted a new architecture centered around two key concepts: a queue of work items and a group of local mode Spark modules that pull from this queue. Their design goals were clear: keep the Spark modules busy, stop them when not needed, and ensure all work items were processed successfully. The final design included several components: file metadata storage, an Amazon RDS cluster running PostgreSQL to manage statistics about incoming files, Work Manager, an AWS Lambda function that periodically pulls waiting files, prepares work items, and publishes them to an Amazon SQS message queue, Work Queue, an SQS message queue for work items waiting to be processed. Processing units, local mode Spark instances running as pods on an EKS cluster, constantly busy as they pull work items from the SQS queue. Metrics Adapter, an adapter that provides Amazon CloudWatch metrics to the Kubernetes Horizontal Pod Autoscaler. Horizontal Pod Autoscaler, This component scales pods based on the number of messages in the queue, ensuring efficient resource allocation. Work completion queue. A second SQS queue for reporting the completion of work items, which are then updated in the PostgreSQL database. #### analyzing the results. The results were impressive. The EKS pods scaled dynamically based on the number of work items, quickly reacting to bursts of incoming data. Performance per instance improved by approximately 130%, all while maintaining consistent costs per gigabyte processed. The new system also boasted a 55% reduction in costs for the same amount of data processed. #### conclusion. Nielsen's evolution from a traditional architecture to a serverless-inspired model on Amazon EKS showcases the power of rethinking established patterns in big data processing. By tackling the core challenges of data shuffle and scaling, they achieved remarkable performance gains and cost reductions, demonstrating the potential for linear scaling in large-scale data operations. If you're grappling with big data processing tasks that can be broken down into smaller, independent components, consider leveraging similar strategies on Amazon EKS to unlock linear scaling and significant cost savings.